Hello everyone. This video is to accompany lesson 1.3. This is a vectors example using the sine and cosine law. John walks 200 meters at north 50 degrees east, pauses, then walks 100 meters east. Where is John located relative to where he started? So I'm going to need a magnitude there and a direction. Now for these kinds of questions, notice that there are only two displacements that John makes. 200 meters and then 100 meters, albeit in different directions. Since we are using compass directions for this question, you have to identify and draw a compass on your page. Okay, so at the very least, you have to identify where north is. You don't even have to put this little cross here. You just need one arrow indicating the direction of north. Generally, it's the top of the page, but you have to still draw it. All right. Now what I'm going to do is I'm actually going to draw the arrows representing this vector and representing this vector. So I have one vector here and I have one vector here. Okay, I'm going to draw one arrow for each of these. Before you start drawing your vectors, you got to know where the vector is going. So you know where to start drawing. So for instance, you wouldn't start drawing your vector in the top left here because I have to go north 50 degrees east. So that means I'm going in this kind of direction. I'm going to be going into the word problem at that point. So I need to start a bit lower. In some problems, you might end up going north and then west off the page. So then you would have to start over here. So try to visualize where you are, where you're going before you start drawing. Here I'm going north 50 degrees east, so like this, and then I'm going east, right? So then I'm going to go like this. So I'm going to end upwards and to the right of where I start, so I'm going to start down here. Wherever you start, draw what I like to call a small Cartesian coordinate system, which really just looks like a large plus sign, okay? And that's going to represent your north, east, south, west, so that when you draw your vectors, you can work out angles and your drawing is accurate. Okay, so the first vector is 200 meters north 50 degrees east. So this vertical line on top is north, that horizontal line to the right is east. So north 50 degrees east. You know that the angle between north and east is 90. Half of that is 45, so the midway point is 45. This is 50, so that's just past the midway point. So what I'm going to do is just go approximately past the midway point. It doesn't have to be exact, but it shouldn't be, completely off either. I'm going to draw an arrow here, and this is going to be 200 meters, and this angle is 50 degrees. Okay. You don't have to draw this to scale. I do want to tell you to use a ruler. That's important so that your picture looks neat and accurate, but you don't have to actually measure this out. Okay, this is about 7 centimeters, but it doesn't really matter. If you want to draw it to scale, you can. But as long as it looks relatively correct, don't draw the 100 meters going to the end of the page, obviously. Okay, so we have our first vector. Now, wherever your first vector finishes, draw another Cartesian coordinate system, so another large plus sign. Okay, and the reason for that is we're going to attach the tail of the next vector onto the tip of this one. The next vector is going 100 meters east. East is to the right. So I'm going to take my ruler and I'm going to draw this going to the right 100 meters, so something like that. Now, if there was some other angle, for example, 100 meters south, 60 degrees east, then this arrow would be coming down like that. Okay, so John starts here, travels up, travels right, and now where is John located relative to where he started? Okay, I mean, this is pretty much what the question's giving us. We're just putting it into a picture. The resultant is from the tail of the first vector to the tip of the final vector. So there's the tail of the first vector, there's the tip of the final vector. So I'm going to go ahead and put in my dashed line. This is my resultant vector. Okay, so I not only have to find the length of that arrow, I have to find the direction. Now, since my displacements, my individual displacements, or rather John's individual displacements, are not just along the northeast, southwest coordinate system, I have to use something other than Pythagorean theorem and SOHCAHTOA. So that's not too bad. I just have to use sine and cosine law, and most of the problems will be like this. So what I need to do, I know that in order to use sine law, for instance, I need to have side angle pairs, which I don't have. For cosine law, I need a side angle side, right? Side angle side. So I don't have the angle in between, but you know what? I can find it. You see this is 50 degrees, right? And this line here, this vertical black line, that's north. This vertical black line here is south. Guess what? North and south are parallel to each other, all right? And so if you recognize this, this is the, some people call it the Z pattern, some people call it the N pattern, where if you have two parallel lines and you have another line that crosses them, this angle here and this angle here are the same angle. It's called the Z pattern or the N pattern. So that means that this is also 50 degrees. All right, now we have to find this angle. Well, this angle, that's the angle between east and south. That's 90 degrees. And guess what? Now I have that entire angle sandwiched between the two sides, which is going to be 140 degrees. So what I like to do at this point is redraw this, but as another just simple triangle. Okay, so what I'm going to do is I'm going to draw it like this, and I have a piece going to the right, and then I have one piece joining the two of them, just something like that. Okay, so I know that I have 140 degrees in between. I know this is a side length of 100, this is a side length of 200. And at this point, what I like to do is label, well, the corners. So have some kind of labeling system. Generally speaking, the corners, the angles are given capital letters, and the opposite sides are given their respective lowercase letters. So opposite of angle A is going to be lowercase a, opposite of angle C will be lowercase c, and opposite of angle B will be lowercase b. So if you notice, the resultant is lowercase b. We're going to eventually need to find that. Okay, right, so let's go ahead and do that. Actually, we're going to do that first. So since we have side, angle, side, we're going to go ahead and find the opposite of the angle using cosine law. If you need a refresher on cosine law, please do review it before looking at this problem. All right, so cosine law, based on this, I know that I need a certain formula. So since I'm looking for b, it's going to be b squared is equal to a squared plus c squared minus 2ac times the cosine, and whatever side you put here, you put the respective opposite angle here, cosine of capital B. Okay, all right, and that's why I need the other two sides and I need the angle. So a squared, a is 100, c is 200, so 100 squared plus 200 squared minus 2 times 100 times 200 times cosine of 140 degrees. All right, so 100 squared plus 200 squared. If you are going to enter this in your calculator all at once, please be vigilant and make good use of brackets. Minus 2 times 100 times 200 times cosine of 140. Keep in mind that number is b squared, so that's 80,000. Oh boy, hard to see at this angle. 80,641.78. We take the square root of that, and so then b is equal to about 284. Okay, now the units for that would be meters, and remember I always say, ask yourself, does your answer make sense? Well, look at these two sides. I got 200 and 100. This green line, or this line labeled b, is clearly longer than those two, and so it would make sense to be 284. All right, so we know how far he is. Now we just have to find the direction. Now the direction you're always going to find using the angle relative to where you're starting. Okay, so based on the original picture, I'm just going to take my black pen here and I'm going to extend this east line out a bit so you can see what I'm going to refer to here. So I just extended that out. What I need is I need this angle right here. Okay, I'm going to call this angle theta, because if I have angle theta, then I can say that John is 284 meters, and the direction, well, once I find theta, then I can figure out another angle. Okay, let me just extend the north line. I can find another angle, and that's going to be this one right here. Okay, I'm going to call this angle alpha. Okay, so there's the alpha symbol, kind of looks like a fish. All right, this one here is theta. Okay, notice that alpha and theta are both measured from one of these compass directions, and they're both going to the same point, the same green line. Okay, so together alpha and theta make 90 degrees. Alpha plus theta equal 90 degrees. So what I want is I'm going to try to find theta. Once I find theta, I'm going to subtract it from 90 and get alpha. So that my final answer is going to be John is 284 meters from his starting point at a direction of north alpha degrees east. Okay, so whenever you see the direction given like this, you start at the first compass direction and you rotate this many degrees towards the other direction. Now, some of you might look at that and say, well, you already have theta, why don't you just say east theta degrees north? And well, the convention is you always put north or south first, and then you put the angle east or west, all right? So that's why I then have to just do a quick step and find alpha. It doesn't take long, maybe a few seconds. All right, now the question is, how am I going to find theta? Okay, so that's the fun part. How am I going to find theta? Well, in order to find theta, the first step is going to be to find A. So let me find angle A first. So this will help me. I'm not going to use blue because I guess that'll get a little bit confusing, but let's find angle A first. Now, since I already have, now this I know is 284, I now have an angle side pair. I can find this angle using the opposite side. That's sine law. Sine law says if you take angle side ratios that are opposite to one another, you can find some unknown hidden within that formula. So since I'm looking for angle A, I'm going to put sine A on the top left. So sine A over A is equal to sine B over B. And you know, you could set that equal to sine C over C, and just as equally, you could take these ratios and flip them upside down if you were looking for the sides. But we're looking for the angle. So sine A, so I'm going to multiply both sides by little a, is equal to little a over little b times sine b. Okay, so all I did is I brought the b under the a when it gets multiplied. But remember, multiplication, division, you can write it in whatever order you want. All right, a is 100, b is 284. So this is one of those unfortunate times where you have to use the information you solved for in your solution because your hands are tied, times sine 140 degrees. Remember, this is equal to sine of the angle. Okay, so you're going to expect a really small decimal. So actually, yeah, let's do it like this. 100 divided by 284 times sine of 140 degrees. Okay, so that's 0.226333665. And I'm going to take the inverse sine of that. So then A is equal to about 13.1 degrees. You can even just call that 13 degrees if you want. A is 13.1. Okay, so how does that help us? 13.1 degrees. So I'm going to write that there, but I'm also, oh, sorry guys, I'm also going to write that here. 13.1 degrees. Oh, so you know what? This is actually a nice outcome of this problem. Usually we actually have to find theta in order to find alpha. But in this case, we actually don't need it. Since we have the 50 degrees and we have the 13.1, we already know alpha. So we actually don't need this time. Okay, so that actually saves us some time there. So if you actually look really closely at the picture, at the end of the day, we're trying to find alpha. And since we already know that part of alpha is 50 degrees, we just need to know this other little angle in here as well. That's 13.1. So alpha is 50 plus 13.1, so that's 63.1. .1 degrees. Now, it's not enough to have the angle. You have to be able to state the direction properly as well. So that's going to be north, 63.1 degrees east. And so our final answer, we have to put a therefore statement. Therefore, John, let me just circle these parts. John is located 284 meters. And I'm not writing on the screen. There we go. John is located 284 meters from his starting point at a direction of, and this goes in square brackets, north 63.1 degrees east. If the question tells you you have to put it to one decimal place or it's specific about how precise your answer should be, follow the instructions in the question. Okay. Put your final answer in a box. That way we know what your final answer is. And there we have it. We have solved a vector problem using sine and cosine law. And I just want to let you all know that with these kinds of problems, 95% of the time, you use cosine law first, just like we did. So you draw your picture out, start by drawing your Cartesian coordinate system, draw your first vector, draw the Cartesian coordinate system where the first vector ends, draw the second vector, draw your result and put in all the values and see if using geometry and just simple triangle rules, you can figure out missing information. And generally speaking, you can figure out the angle between the two sides. Once you have that, redraw the triangle, label the corners with capital letters, label the opposite sides with the associated lowercase letters, and then you're going to go ahead and use cosine law. Always, always write the formula first, plug in the values, figure out what that length is. And then in order to find the direction, you usually need that angle inside. So then you use sine law to find the angle inside. Write the formula first, properly rearrange, find it, and then based on that final answer, work with the original picture to figure out the direction. So we did that, 50 plus 13.1. Put your final answer in a therefore form and in a box. And you're done. Hopefully that's okay. Stay tuned for another video. That's going to be a vectors example, but solving it using resolution of vectors.